So for a typical Cortex-M device, then the startup code could either be written in assembler or C. It's usually provided for you by the MCU vendor. And what would normally happen when he boots up is it will jump to address 0, and then at address 0, stack pointer gets set, and it jumps to a reset handler. Okay, so typically you don't need to worry about the code. It's provided for you, but you might want to look through it to see what's actually going on. The system init function is going to also be provided by the vendor, and it will do things like initializing the clocks and getting the other hardware ready to start executing code. The reset handler itself might do things like copying data from read-only memory into RAM. So once it's initialized the memory, it's finally ready to call some further code. So it may call your main function directly, or there may be a little block of code provided by the vendor in their library to call your main function. And then your main function will be the starting point for your C application. So it's interesting if you have a chance to step through in a debugger and look at what's actually happening as your code gets reset. So the main function is where your program starts, and with an embedded system, your main function, let's say, is running on startup. There's no operating system that's going to launch your main function, so your main function doesn't take any arguments. Within the main function, there may be some other initialization functions which you may write yourself, or they may be provided by the vendor. So, for example, there could be a board support package that's provided by the vendor in their software development kits that's responsible for initializing the various peripheral devices that are part of your embedded system. And then usually there'll be some kind of loop. So we'll go into that loop, and that will be an infinite loop where your code runs forever until you turn the power off or reset it. So we don't, strictly speaking, have to have a return value. So you can put the return value in there if you like for good practice, but you should never reach that return statement. Okay, and it's not like a regular C program where at the end of the program you return back to the operating system. So just to summarize, there's no arguments passed into main. We've got a block of code for initializing peripherals, and then we've got our application, and the code never returns. So in terms of accessing data in memory and registers using C, that's also fairly straightforward. So the memory will be divided into various regions, and there's a region known as the BSS region that's the place where your static variables are going to get stored. So if we have static variables and those variables have not been initialized explicitly, then they get written into the BSS region and they'll be automatically initialized to 0 by the startup code. And that applies to static variables which are global. If you have static variables inside a function, again, those will also go into the BSS region. You might have some static variables that get initialized. Okay, so those still have to be stored somewhere and set up before your code executes. Well, those go into a similar area of memory of RAM known as the data region. So the BSS and the data region are both used for static variables. The BSS for variables that aren't initialized, so they get initialized into 0, and the data region for any variables that have explicit initialization. Finally, you may have some variables which are const. So the const keyword means that they're going to be read-only, so that can be recognized when your code is built, and those can be put into a dedicated read-only region of memory. So that could be part of the RAM, or it could be put into flash. So it depends on the settings and the tools that you're using. If you want to find out where everything has been placed in memory, then we can take a look at the linker map file. So when you run the linker, it generates this map file, and the map file gives you the memory layout in terms of where each function, each static variable has been placed in memory. So we see, for example, the main function that goes into the text region. So the text region is where your code is placed. And we can see the sort of starting address of our main function. So again, if you ran through your code in a debugger, you set a breakpoint on the first line of main, then it would correspond to that address. For your data, then we've got our read-only data, and we can sort of see the name of digits and the address where that has been placed. We've got our var-B and var-C. They're in the data region. And again, we can check their addresses, and we can look at those in a debugger to confirm they have the expected values. And then finally, var-A goes into the BSS region. And again, we can check its address. Now, most of the variables that you use inside your application are allocated differently in terms of memory. So variables that are declared in a function get stored on the stack. And the stack grows and shrinks automatically as the variables come into scope and then go out of scope. So memory allocation is maintained by the C program itself. So if we have our stack, which is typically sitting at the top of RAM, in our main function we could check to see what the stack pointer currently is, again using our debugger. If we then stepped into function f, when we get into function f, then you may notice that the stack actually has new values written to it, so that will include things like any registers that need to be saved, the return address, so the program knows where to return at the end of that function, and for our discussion here, a block of memory that's going to be used to represent any variables which are going to be used inside that function. Okay, so in this case we've initialized the variable, so you would see that initialized variable inside the stack after executing that line of code. At the end of the function, then the stack pointer is returned to its previous value, so information that was used inside that function f is still on the stack, but we can't guarantee it's not going to be overwritten by anything else, because the next function that gets called is going to overwrite that data. So if you've got pointers to automatic variables, you need to be very careful, because if variables are no longer in scope, that stack location might be used by something different. So you need to check to make sure that you don't keep variables, you don't keep pointers that hold the address of variables that are no longer valid. So that would be a case where if you had a pointer to this variable, make sure you set it to null so it can't be reused inadvertently. So that's the sort of bug that can very easily creep into a program, and the compiler won't give you an error message if you have a pointer to a variable that's no longer in scope. So pointers are particularly useful in embedded systems as a mechanism for accessing hardware. So we can access any variable, but importantly any register whose address is known. And for ARM Cortex devices, that's particularly useful because everything is memory mapped. So all the registers for peripherals have a memory location. It means that we can access those using RC pointers. The only thing you have to remember is that the type of that pointer must match the size of the object that you're going to address. So here's an example in our data sheet for the particular microcontroller. We can see that there are various addresses for peripherals. So in this case we've got the GPIO, the general purpose input-output, and we see that there is a port data output register sitting at address 400F F100. If we wanted to access that inside the C program, we could simply declare a variable, which is a pointer. It needs to be pointed to a 32-bit value, so we could use a uint32t type as to represent that. So GPIO PDOR would be a pointer that points to that memory location. And we need to tell the compiler to treat that memory location as a pointer to a 32-bit integer. Having created that variable, we can then simply dereference GPIO PDOR whenever we want to check or write to the value of that register. Okay, so here we're just writing a 1 to every bit by writing the value FFFF. Okay, so it's very easy to use pointers for that purpose. Now, not all registers are going to be things that you want to write to. There may be some registers which are read-only. So we've got here an R indicating that the port data input register is read-only. Now, if we take the same approach as on the previous slide and declare a pointer that's going to point to that data input register, and then we've got a loop that's going to be waiting until a particular bit 5 in that register gets set, then we may not find it behaves as expected. The problem is that the compiler may recognize that you're only ever reading that location. So if you're only going to read it, then for optimization purposes, then the compiler might say, okay, well, I don't need to read it every time around that while loop. I can just read it once and then insert some code that depends on the value. Well, that's not going to work as expected, because we're expecting our while loop to be sitting there constantly reading the value of that register until the contents changes. So how do we prevent that optimization from breaking it? Well, we need to add another keyword. And the volatile keyword is designed for exactly this purpose. So if you have variables which are going to change outside the control of the C program, then they should be declared as volatile. And that's exactly what we have if you have an input port, because the input port is going to be changing without the compiled code doing anything. So making that simple change, declaring the pointer as volatile, in this case we're just using a type def to make the code a bit simpler, we now get our correct operation in the sense that we have a while loop that's now waiting for that value to change. What about other registers? So what if we want to write some code that depends on a register that's part of the CPU? How can we do that in C? Well, we can't use pointers here because the registers in the CPU don't have addresses, so a pointer's no use. But embedded systems would typically provide other mechanisms for that sort of activity. For example, with the ARM compiler ARMCC, you can add a special extension to indicate that you want to access, in this case, the MSP register. Alternatively, you can actually write inline assembler using the C compiler for embedded systems. Okay, so there will be a special syntax, and again, look at the instructions for your chosen compiler to find out what that syntax is. So again, here with ARMCC, it's just __ASM, and then we can have inline assembly language instructions that can access the CPU registers that we need, and that can just be part of some standard C function.
Doulos is a training company providing expertise and specialist training worldwide in all of the areas you can see on screen, from SoC design and verification, FPGA and hardware design, to embedded software and Python and deep learning. You can watch the rest of David's webinar, Why C is the Language of Embedded, whenever you want, by heading over to our website www.doulos.com/od and registering for free. For more free tips and tutorials, visit the Know-How area of our website, and don't forget to subscribe to our YouTube channel. Thanks for watching.